So this is the 10th tutorial about fluid mechanics. We are leaving fluid statics now and we start to deal with fluid flows. Bernoulli equation is really important before the midterm. Bernoulli equation is really important before the midterm. And Bernoulli equation is really important before the midterm. It is really important so that I am repeating it 3 times. But when shall we apply Bernoulli equation? You must make sure that these 4 conditions are satisfied before you apply the Bernoulli equation. First, you must make sure that the viscous effect can be neglected. For the second one, you know what is incompressible assumption. That is, density does not vary with pressure. So most liquids are incompressible. We are safe if the fluid is liquid. But this assumption is also valid for gases when the pressure variation is small. We shall see this later in an example. About the third one, some of you have already heard about steady condition. To describe something as steady, it does not change with time. A more rigorous definition goes this way. A quantity x is said to be steady if partial x partial t equals 0. In fluid mechanics, a flow is steady if and only if partial v partial t equals 0. That means, if the velocity field does not change with time, then anything associated with the flow, it does not change with time. It does not necessarily mean that the particle does not accelerate. It is because acceleration can still be a function of position. We shall cover it later in this video, and there is an example about that. So we are done with this one. For the last one, what is streamline? Streamlines, by definition, are lines tangential to the velocity field. So if we have a velocity field go this way, then we have these 2 streamlines. We are going to work on that in the next chapter. Under steady conditions, streamlines are just trajectories of the particle or path lines. Imagine we have a particle here. If the flow is steady, this guy will go here after some period of time. So I repeat, you must make sure that these 4 conditions are satisfied before applying Bernoulli equation. Professor Lee told us that we will obtain 0 mark in the midterm if we abuse Bernoulli equation last year. If you are really interested in knowing why these conditions must be satisfied in applying Bernoulli equation, you shall go to lecture and derive Bernoulli equation once yourself. There are 3 forms of Bernoulli equation, and you may use whichever convenient to the problem. In fact, I've talked about the first form in the tutorial 2 already. The first term here measures the flow work, the second term is the kinetic energy, and the last one is gravitational potential energy. Although the book uses Newton's second law to derive the formula, the Bernoulli equation can be thought as energy balance. If we multiply the first one by the density, then we get the second one. So each term here has the same unit as pressure. People call the first one as static pressure, the second one as dynamic pressure, and the third one as elevation pressure. And people call this sum as total pressure. But I have one thing more to talk about this version. If the flow is horizontal, then the elevation pressure goes away. Then the total pressure is just the sum of these 2 terms. Then points with the 0 velocity has the highest pressure. In fluid mechanics, points with 0 velocity are called stagnation points, and their pressure are called stagnation pressure. And that pressure is simply the total pressure, and it can be evaluated using sum of these 2 terms at every point. Finally, if we divide the second one by the specific weight, we get the third one. And now each term here has the unit of length. People call the first one as pressure head, the second one as velocity head, and the last one as elevation head. We now do a quick example to illustrate how to use Bernoulli equation. Before applying Bernoulli equation, we must ensure that all the 4 conditions for Bernoulli equation is satisfied. First, we have negligible viscous effect, and we have steady, and also we have a long streamline. But what about incompressible? And we just say this one is okay because the change in pressure is just 20 Pascal. We will further justify for that in the last part of the video. So we now write down the Bernoulli equation. And that means for points 1 and 2, and we substitute in the values. So we have, and we continue to solve for V1, and we are done with this easy example. As I said previously, as you are going to learn in chapter 4, acceleration is the material derivative of velocity, and that is not equal to partial v partial t. Even if this term is gone, you still have this term. And in streamline coordinates under steady conditions, the streamline component and the normal component of accelerations are given here. And this figure below shows that how the two components affect the shape of the streamlines. In fact, the Bernoulli equation can be manipulated to obtain information about streamline component of acceleration. We now do a quick example about that. So we have water here. Water can be assumed as incompressible. And we further assume that the flow is steady and all viscous effect can be neglected. Now it's a long streamline. So all the assumptions has been fulfilled. A Bernoulli equation we write down and we differentiate it with respect to the streamline variable. Now the pipe is horizontal, so this just go away. And this term is the streamline component of acceleration. So we write down, so we have and this is the pressure gradient required to accelerate the fluid. Now for interest, in fact, for compressible flow, we could use a weaker version of Bernoulli equation. This equation is also true for compressible flow. To see why, you have to go through the definition of Bernoulli equation. For gases, we have the ideal gas law. So this term equals, and that is, and we integrate. So we conclude that the gas version of Bernoulli equation is just, this formula is just true for isothermal process. Now we see why the incompressible assumption is appropriate here in the first example. First, we compare the density. From the ideal gas law, we have P directly proportional to the density. So the density at point 2 is, and that is just a small difference. And from the previous formula, so we assume this process is isothermal, and we continue to write down our formula. And we substitute in the values. And solving for 3-1, we get the same answer. With such a small difference in density, the answer is just the same with the two different versions of Bernoulli equation. In summary, today we discussed the limitations of Bernoulli equations. We look at the three forms of Bernoulli equation, and we also look at the concept of acceleration along streamline. We also worked through two examples about that. Hope you enjoyed today's tutorial and thanks for watching. Feel free to ask us any question and give us any feedback in the comments.